Good morning, everyone. Thank you so much for attending this session. My name is Patrick O'Mullen. I'm an undergraduate student majoring in physics and computer science at Worcester Polytechnic Institute. And I'm here to talk about the research I've been working on under the guidance of Dr. David Wittman from UC Davis, starting at their REU program this past summer. The research concerns reconstructing the dynamical properties of galaxy cluster mergers using radio relics. So let's talk about a little bit about what those things mean. Interested in studying these mergers is due to the unique window of opportunity they provide to observationally constrain the properties of dark matter. Specifically, dark matter's hypothesized self-interaction cross-section. If you look at the key in the bottom left corner, you'll see that this diagram can be split into different categories of objects. The purple being dark matter and gas, the blue being dark matter on its own, red, gas, and little sprinkles are galaxies. And so in these systems, if we regard dark matter to have zero interaction cross-section, then we would expect that they're collisionless, not exchanging momentum. And the same can be said for the galaxies, as they are going to pass through each other and not actually exchange significant momentum, unlike the gas, which will have a cross-section and interact with itself and exchange momentum at the center, hence why it stays in the middle. So if we think that it has no self-interaction cross-section, then we should see it observationally wherever the galaxies are. However, if there is some sort of cross-section, we should see some exchange in momentum that would result in a non-zero offset for where we actually find the dark matter pool versus the galaxies. And that's what you see in this second figure here. Comes, how are we going to make sense of these things that we're seeing? And so first thing you got to do, obviously, is you want to understand the context of the system that you're looking at. Where is it in the merger phase? How long has it been since the first passing? How fast were they going? How big are the clusters, right? So there's some things we can observationally notice right away. If it has radio relics, which we'll get into what those are a little bit later, those are directly observable. What you're looking at now is CISA, or the sausage cluster, a very well-studied cluster. You can see the gas towards the center, as well as the two massive subclusters. And so obviously with a lensing analysis, you can figure out the respective masses of these objects. You can look at their relative distances to one another, etc. And that will give you a nice insight into sort of some of those directly observable properties. But that leaves a lot of variables that would dictate this evolution of the system unknown. For example, with what viewing angle are we looking at it? Is it in the plane of the sky? How long has it been since the initial crossing? What was their maximum speed? Questions like this need to be inferred through different methods. Used to actually try to infer these parameters, usually with stage simulations of some kind. The first is n-body simulations. So this is when you have particles that are confined to a geometry and they have a set rules governing their interaction and therefore the system's evolution. This is commonly used with dark matter only. You have magnetohydrodynamical simulations, where particles considered include baryonic matter, as well as the corresponding interactions in the presence of and generation of magnetic fields, which is much more complicated situations. And these can occur at smaller scale when you care primarily about the finer details of the object of interest, so like the small scale structure of how matter is distributed. But it also can be on the large scale where you're really interested in the cosmologically motivated set of parameters that actually dictate the large system's evolution. Had explored making use of large cosmological n-body simulations, specifically one called Big MDPL, to use that to record the dynamical properties of various analog clusters that were simulated in the system. From these analog clusters, you could keep a record of every single parameter and therefore use it in comparison to analyze real-world observations through some statistical techniques. And from that, you could infer some non-observable parameters. So what you're seeing here is a animation of a large cosmological n-body simulation. And what you see here is the various tracks of different analog candidates for a specific observable cluster. And you could see, as this is a measure of their separation from one another, and when they peak at the bottom, that is when they cross at pericenter. And from this, as well as many other properties, you can derive various interesting needed information regarding this system, such as the time since the pericenter. You could derive the maximum velocity, the velocity angle, so the offset between the separation vectors, the two subclusters, and their current velocity, as well as the viewing angle with which you're looking at the system. So my work has looked to extend this existing method to consider radio relics, which are a sign of shock location. So radio relics are essentially regions that are very highly polarized in the radio frequency, and they form at the outer areas of clusters, and they're thought to be formed by diffusive shock acceleration, which is a first-order Fermi acceleration. And so why these are useful is because they're going to tell us a few things about how the system's oriented, as well as they provide some nice context to where we are looking at the system in terms of its current state. Before, one of the big things that radio relics will provide us is a nice way to estimate the merger phase of the situation we're looking at. So if you can look at the first top figure, you can see 4 panels. In the first one, you have pericenter, where the clusters just cross each other. The second, you have the outgoing scenario after they passed each other and generated the shock front. You can see the radio relics represented in green, moving monotonically outwards. You have apocenter, which is where the clusters themselves cease to move outwards and begin infalling again, and the returning scenario as they are currently infalling. And if for a moment, if you ignore the presence of the radio relics, you notice a symmetry between the outgoing scenario in terms of observational positions and the returning scenario. Just by spatially resolving these two situations, you cannot tell whether a cluster is in its outgoing or returning scenario very easily. You can estimate it using other known parameters, but there's a nice way to look at the radio relics, as they provide context. Because they travel outwards monotonically with time and slow down with some degree, but not significantly, you'll actually notice that in the outgoing scenario, depending on however fast they were going, they're going to be much closer than in the returning scenario. So what's nice about this is we can take our simulated analog candidates and we can build distributions for where we'd expect to find their relics and compare that against our observed location in the real world. So for this investigation, we picked 3 different metrics that could be used to try to build these distributions. The first was the relic to relic distance, how far apart they are. The second was the relic to its closest cluster. And the third was the other relic to its closest cluster, provided that there are dual radio relic systems. From this, we can plot our observation on a position chart and build up a distribution. We can then marginalize over different viewing angles, as well as considerations of how far the shock front should have propagated outwards. And we can build one larger distribution of these marginalized samples and their measurement in terms of their likelihood of a match for a candidate to be an analog system. After this, we can plot the intersection points between our observation and the 2 curves, which gives us 2 data points for the likelihoods, respectively, of it being returning or outgoing. And we can generate a very simple metric where you just have outgoing means that the ratio is more than 1, indeterminate is around 1, and less than 1 meaning returning. Really nice thing about these relics is that there are several radio studies on the spectral properties of several systems, and with some good data, you can actually use those to create a lower bound on the viewing angle. That way, we can consider more systems in the range of realistic scenarios rather than exploring viewing angles which are physically impossible based on the measurements we receive. This relationship where we assume a strong field and we can relate the viewing angle to the polarization measurements. Here we have R representing the compression ratio of the shock front. Gamma would be the spectral index of the electrons in the system at the shock front. And as you can see in this graph, a measured polarization corresponds to a minimum limit on the viewing angle along this curve, which is really useful. So to evaluate this method, we explored CISA, the sausage cluster, as well as the bullet cluster. For CISA, we looked at the polarization technique as well as included all three metrics for the relic distances. For the bullet cluster, because it's primarily been observed in the X-ray region, we did not perform the polarization analysis on it because there was not an abundance of data. However, we did make use of the known shock front location and its distance from its nearest cluster to make an estimate for the relic argument. We have a roughly 55% polarization. Most of the literature seems to agree that it's between 50 to 60% polarized. We have a radiospectral index of the electrons to be about 0.77. This would correspond to a compression ratio of 6.56 and a spectral index of the electrons to be about 2.54. And so when we actually put in our polarization measurements to this function, you can see that we output about a 64.1 minimum viewing angle, which agrees with most known observations on the system that it's roughly within 30 degrees of the plane of the sky, which is a good result. Analysis for CISA, we have observed separations of the radio relics to be about 2,600 kiloparsecs. We have the distance between the northern cluster and relic to be about 850 kiloparsecs. And the southern cluster to southern relic is about 450 kiloparsecs. So when building up these distributions, as you can see in the graph, this corresponds to our ratio for the relic to relic distance to be about 1.366, for the northern cluster to relic 8.467, and the southern cluster to be roughly 0.0047. So we have two of our metrics somewhat leaning, or one of the metrics leaning ever so slightly to be an outbound cluster, although not very strongly as it's quite close to 1. One of our relic to subcluster metrics leans favorably in the distance of outbound. However, our other corresponds to a more returning scenario. So overall, there's some ambiguity in what phase CISA is in, but it tends to be agreed that it is at a stage where it's past its first paracenter. So this is in line with that opinion. About the parameter extraction. So on the left, you can see the familiar chart for CISA. Each one of these lines is a path taken by an analog cluster through time, where again, the peak at the bottom indicates first paracenter crossing. And so you can see opacity is an indicator of the likelihood of that cluster being a good match. So the bright red cluster is one of the closest matches, whereas some of the fainter blue or purple or green clusters are a little less like the actual real-world observation. You can see on the right-hand side, we have some estimates for the time since paracenter in mega years, as well as Vmax for the maximum velocity. You can see that we have for 95% confidence intervals here, and the time since paracenter sort of agrees to be a little bit below 1,000 mega years, probably closer to 500, and the maximum velocity appears to peak somewhere around 2,400. Very brief analysis on the bullet cluster. So specifically, you have two subclusters in this system. You have the bullet, which is the smaller cluster, and the main cluster, which is most of the mass. And there's known about 80 parsecs out away from the smaller bullet cluster, there is a known shock front. So due to a lack of radio analysis or strong radio relics, the analysis we performed was just using the known shock front location at a separation of roughly 80 kiloparsecs. And so this yielded a ratio of 11.29. And as you can see in the graph on the right, this strongly favors an outbound scenario, which is matching in line with what the common consensus is with the bullet cluster, that it is a outbound system. Again, here you can see the parameter extraction for the bullet cluster with the various paths taken by the different analogs, as well as some estimations on time since paracenter and maximum velocity, where we have a time since paracenter peaking a little bit below 500 mega years, and you have a Vmax somewhere between 2,000 and 3,000, which is consistent. We found that the distributions and results that we get from this method largely agree with some of the other results derived from other simulations and observations. So it does reproduce some very reasonable values. However, there are a few things to note in future work. While this is most certainly computationally much less intensive to run the analysis, we are using a purely kinematic estimate for where the relic should be, and that's going to neglect certain motivators such as magnetohydrodynamic origins for some of the dictation of the system's evolution. So that is a bias that's absent from our sample size. So it's possible that it might be worth resimulating certain analogs from the large-scale system to include these effects and then perform the analysis on that. Additionally, there seems to be a large population in terms of analog samples that are outbound compared to those returning. So it would be interesting to explore using larger n-body simulations on a larger population. So at the RU program at the University of California, Davis, and funded by the NSF. I'd also like to thank Dr. David Wittman for his willingness to provide me with this research opportunity, as well as his guidance and support throughout this project. And here are the references used for figures as well as the data.